Hi all. Uh, from the last office hour, I got few students who are facing challenges to understand this problem. This is the problem number 4 from problem set 1. And even from the quiz, I found few comments where they were asking questions. Few students were asking questions related to this. So I thought of solving this and recording a video and post it on Canvas so everybody could get it, that even whoever is not able to come to the office hours will also able to understand this concept, because this problem has two different concepts in it. And yeah, I wanted to make it clear to all, so let's get started. So okay, so let me draw this first. Okay, so the problem says we have a tank. We draw a tank whose height is like 5 meters, like 5 meters high, and the height is like 5 meters. Then the length of the tank is 2 meters. This length is given 2 meters, and width is again 2 meters. Like it is going into the tank, so it should look something like this, which is again not shown in the figure. So it's something like this. Yeah, this is again 2 meters. And it said there is a square window. Yeah, it said square, right? So there's a square window on in front of the tank somewhere over here, whose sides are like zero point 0.3 meters, 0.3 meters. As it is a square, all sides will be same. All sides are like 3 meters. May not look like a square in the drawing, but it is a square. Then the top edge of the window is HT. It's given. This is HT, which is 3.85 meters from the water surface. I think it's filled with water. The entire tank is filled with water. Okay. Then yeah, the outside window is exposed to the atmosphere. Yeah, this is exposed to the atmosphere, so you can get air pressure from the top. Yeah, and these are the constants like the density of the water, which is the acceleration due to gravity, and the atmosphere pressure is 101 kilopascal, which is the SI unit of pressure. Okay, all these things are given to us. Now, before moving, the first question it asks the find the gauge pressure at the top of the edge. So let's talk about the hydrostatic pressure. I'll just briefly explain what hydrostatic pressure is. So let me go down here. Uh, yeah, hydrostatic pressure means if you have a tank, okay, it has water in it, filled with water, and it has a certain height. Take it is like again, let's take 10 meters. The height of the tank is 10 meters. Okay. So if you see from the top, the value of h at this point is 0, right? Because it's at the top of the tank. You go to the middle, the value of h will be around 5, and at the bottom, the value of h will be at around 10, and all are in meters. So to find the pressure at uh, any height, formula is the pressure, hydrostatic pressure due to the water is rho g h. Rho is the density of water, which is constant. You can see here, which is already given. G is also constant. It's the acceleration due to gravity. Only thing which changes is H here. Okay. So pressure at this point will be rho. Let's take it P1. It will be rho G. Take it 1, 2, 3. H1, H2, H3. So H1, which is 0, right? Already know it's the top. So there is no water on top of it. So it's 0. So pressure at top is 0, right? And pressure at the middle part would be P2, will be rho, sorry, yeah, rho G H2, which is H2 is 5, so it will be 5 rho G here. And at the bottom, P3 would be rho G into 10, so it will be 10 rho G. As you can see, as you increase the height, pressure increases, right? At the top, there is no water at any point above this point. So pressure at this point due to water, hydrostatic pressure at this point, top of the tank is 0. At the middle, we have around 5 meter of water column. That's why the pressure is 5 rho g. At the bottom, we have around again 5 plus 5, total 10 meter of water column. So pressure is highest over here. So it's 10 rho g. So we found out like as you move from top to bottom, pressure increases. And you can think this as an analogy of, let me draw something here. Think it like a stack of bricks, right? A stack of bricks. Pardon my drawing. It's not good, but still, yeah. So a stack of bricks. So if you find pressure at this point, means the force due to the weight of these bricks will get something around. Let's take it. Let's take it. Let's take the pressure at this. It's like 5 meters, and bottom is again 5. The total height is around 10 meters here, just like our tank analogy. So as you move from top to bottom, think you're just standing over here or something like that, or putting a pressure meter or putting your hand inside it here. Okay, you're putting a hand at this point. So you'll feel some pressure, but it's not more, right? But as you move down, for example, you are putting hand over here, so there is no brick on top of you. So you're not going to feel any pressure. It's not going to hurt. There is no force. So there is just air on top of it. There is no force. When you put hand at this point, you're going to feel the pressure, feel the force because of these bricks. When you move down, again, when you put hand at this point, you're going to feel more pressure or more force because you have more bricks on top of your hand, right? And again, when you go to all the way to the down, when you put your hand here, you're going to feel the most force, the most pressure because you have like a lot of bricks, around 10 meters of bricks on top of your hand. So you're going to feel the force or the pressure more at this point. So we found out like as you move from top to bottom, pressure increases, right? So this is the thing you need to understand, uh, hydrostatic pressure. Now moving forward, so you'll use this same analogy to solve the first problem. So yeah, it asked uh, the gauge pressure at the top and bottom edge of the window. Okay, so let's see if I could copy this figure. Hmm, put it here somewhere. No. Okay, okay. Okay, this will do. Uh, Give me a second. Let me copy it properly so that I don't have to draw it again. Put it somewhere here. Yeah, which will help. Okay. So the question asked, let me get the question again. What question says, yeah, okay. The question says, uh, gauge pressure at the top edge and the bottom edge. Top edge, we know the height from the top edge is already given 3.85. So the gauge pressure will be Pg. We know the formula of hydrostatic pressure is rho g h, right? And we know the height, right? So the height of the water column above this point, top of the top edge of the window, so which is rho g h e. And we know all three of these values, which is 1000 times 9.81 times like 1000 times 9.8 times h is 3.85. We'll just multiply these and get our values. And again, kilopascals or pascals is assign it. Okay, this is the top one. So let me write E gauge pressure at the top edge of the window. Now, what about the bottom edge? So from this diagram, you can get the height of the bottom edge as well. This is the bottom edge. So top edge is 3.85. We'll just add this side, which is 0.3. So the bottom edge height from the top will be, its top of the water surface will be P gauge pressure at the bottom is equal to rho g h, where h here will be h3 plus 0.3, right? Because this is the height of the window, we already know. Just need to add this height plus the height of this edge of the window. So that will give us some value. We know this value, which will be rho g is 3.85 something plus 0.3. You know the values, we'll just put them and get the answer again in Pascal. Okay. These two were the part A. The part A. Now coming to the part B. Part B said the absolute pressure at the bottom edge. Now, how do you find the absolute pressure? B A B S. Let's take it absolute. We know we found pressure due to the water surface, but what about the air? The air surrounding us is also a fluid, right? There's the pressure because of the atmosphere above us. We're going to feel the pressure of that, and it will also going to change as you move above the atmosphere, like as you move above the surface of the earth. Uh, think of this the surface of the earth. So as you move up, is the think this is the atmosphere. So as you move up, there will be less and less air above us. So pressure will going to decrease. Something like uh, tank analogy. So at this point, the atmosphere pressure is given to us PATM, which is 101 kilopascals. So the absolute pressure will be the atmosphere pressure plus the gauge pressure. And we are asked to find the gauge pressure at the bottom. So it will be the atmosphere pressure is 101, sorry, it's 101 plus the gauge pressure. We're going to find whatever value we're going to find from here, and we're going to add these two values, and we'll get the value answer in again in pascals. I think that, yeah, that is the second question. Now the trickiest one, the third one. Here it's asked us to the question asked us to calculate the net hydrostatic force on the window, on this window due to the water. Okay, so let me draw the figure again. Let me get this figure. Okay, this is the figure we have, but let me draw it. Okay, this is the figure we had. initially. Okay, this is the tank and this is the window. And the all the heights and everything were given. But what if you're going to see it's from this side? How it's going to look like when you see it from this side? Let me draw it in 3D. So yeah, it is something like this, right? It's a tank, has some width. How it will going to look like from this side? So if I draw it, let me draw it here. Once you're viewing it from this side, so it will look something like this, right? May not be accurate, but yeah, something like this. And this is the window we were talking about. Okay. Now it has water inside. Has a lot of water inside, completely filled with water. Now I would like to introduce another topic which is called Pascal's law. Let me quickly talk about that here. Pascal's law states, this is the Pascal's law. So the Pascal's law states, Pascal's law, this law states when there is a pressure change applied to a confined and incompressible fluid. Here, in our case, water is incompressible. You can't compress that, right? It's not like air, which can be compressible. It's incompressible fluid. So when you put pressure on an incompressible fluid, which is inside a confined container, for example, we have the confined container, which is a tank. It's not allowing the water to go out, so it is confined. Fluid pressure is transmitted throughout the fluid. Okay, in all direction equally, undiminished. You see here. So the pressure will not going to change. It will be exactly equal at every point inside the fluid. So now if you incorporate that concept here and see this window. So we have water inside the tank, right? And in our previous question, we found out the pressure will change at each and every point. So at this height was like 60 or something, right? Top edge of the window. So the pressure at this point will be how much? We already found that rho GHT. So according to the Pascal's law, the pressure will be exactly same throughout this point. I hope you understand. Like this is a slice at this height. So if you move anywhere in the tank at the same height, you're going to feel the exact same pressure, which is rho GHT, and also it will be applied towards the walls, right? Because it's the same pressure. It said like it will be equal throughout all the directions. So at this height, pressure will be rho GHT, bottom and top, and it will putting the equal pressure on the top and also to the walls of the container. This is very important for this question because this is the pressure experienced by the wall of the container, right, at this particular height. So the height of HT, we're going to get the pressure. So let me draw that again. Let me draw it again. So if I draw a slice from this water column or water volume and which whose height is around P from the top. So the pressure will be rho GHT towards everywhere in all directions. So this fluid element will going to put rho g ht pressure throughout everywhere, like on the walls of the container. Okay. From this analogy, you can get it. The wall, the no, the wall. There is on the wall of the tank. We have a small window, right? So this window will going to experience a pressure of rho GHT, right? Because it's height of HT, and according to Pascal law, pressure will be equal in all directions. So the wall of the beaker on top of the window will also going to experience the same pressure. Similarly, what if you're going to move to the bottom? The height is around. Let me erase this. What if you're going to move to the bottom? Is HB. Again, the pressure will be exactly same in all direction, right? Which is be rho G H HB, and this is the pressure the walls of tank will going to experience at this height, right? So yeah, so this was the concept I wanted to explain. For moving to the question. So the question said, question number 3. Now you can move to the question. This was the question. Now, how do I increase the font size? Let me increase the font size first. Yeah. Mm, yeah. Now I think it's visible. Okay. So this was the question number C, where it asked the resultant net force on the window due to the water. It asked us the force. So how do you find force? We know pressure is force per unit area, right? Amount of force we get per unit area. So from this relation, you can find the uh, force. If you know the pressure, if you know the area, you can find the pressure, right? If you can find the force, right? So you just need to have to find the pressure, which we already guessed. It should be something like this, related to this. So let's do that. Now let me get a good view of this. Let me draw it properly. This window. I'm just drawing this window. See the window from a side view. It will look something like. Let me draw it. Mm, it will look something like this, right? I'm just drawing this window, not the entire tank. The tank is like something like this. I'm not drawing the tank. It's just the window. Okay. So we found out we'll have a pressure of rho g ht at the top of the window, and at the bottom we'll have rho g hb at the bottom, right? So the pressure is changing throughout. Okay. And find the total pressure. Like if you get the total pressure on window and you multiply with total area, you'll get the total force, right? But we cannot find the total pressure because we don't know the pressure in between any point of this window. We just know the pressure at the top and at the bottom. Okay, see, we just know the height of this point and height of this point. We don't know any point in between this, right? To do that, we're going to take help of integration. So here what we'll do, we'll take a small area. This is the window. We take a small strip whose height is like dh. I draw it again. Dh. Okay, and you already know the side of the window, which is already given here, as you can see. Side of the window is given, which is A. Let's take A, and the height at which this strip is present is, let's take it h from the top. Okay, like the strip with its DH, and it's situated at around outside from the top. Okay, so you can find the pressure here, right? Feel the pressure here. Rho G H, because it's at the H side from the top. There is H height of water column on top of this strip. Now, what will be the force here? Force is what? This is the pressure you got on this small strip. Let's take it PS or something like that. Now, the force will be PS times the area, right? Now, from this strip, you can find the area. We know the length, or you can talk this is the width and this is the length. So the area is always length times width, right? Which is here the length is how much A and the width is DH, right? So we got the area. Now we'll just put these values here. So the force will be we know the pressure rho G H, and the area is ADH, right? And please notice this, we took H as a variable, okay, and DH is the very small width of the strip. So this H can change. So we're going to talk about that. So now find the total force from top to the bottom. We're going to integrate it. We're going to integrate it. We know the bottom height, EB. We know the top height, it's around ST from the top, and this can vary from this H can vary from HT to HB. So now what you're going to do, take the limits HB to, we'll start from HT, right? So we'll start from HT and go up HB, bottom height, right? So if you think logically, we're doing nothing but just adding the force on these small strips, means that there could be many small strips, right? Because a lot of space in between these. So just adding the forces on these small strips from the top to the bottom, right? So we're going to uh, first put the total force on this strip, then on this strip, then on this strip, then on this strip, and then on this strip, and you'll add total force. To get the total force, you're going to add the total forces acting on each of these strips. And in this way, you're going to get the total force. So we got this formula. I hope you understood here. Then the force will be, I'll just write it again. It's B, it's T. Here, rho, G, and A. These three are constants, right? Right, like rho is the uh, density of the water, G is the acceleration due to gravity, which is 9.8, and A is again side of the uh, window, which is again constant, which is given, it's not going to change. Only the variables are H and H. H is the variable. So we can take the H out. I'm sorry, the constants out, rho Z A out. Then you can just integrate it from HB to HT, HDH. Right. Now the integration of HDH will be H square by 2, and the limits are H from HE to HB. Now rho Z A times, putting the limits, it will be HB square minus HT square by 2. And you already have all the values. We know the value of HP, it's around 4.15. This value is around 3.85. We know all the values. So after putting all these values, we'll get the value of force in Newton. So that is our final answer. So this question has two key concepts. First one is the hydrostatic, like the pressure changes as you move from top to bottom, right? Because there is more water column on top of you. If you imagine like there is a stack of bricks, I gave you this analogy to understand it better. And the other one, the key concept was here, the Pascal's law. Okay. because at every height there will be the pressure, and pressure will be equally distributed throughout the fluid in all directions. That was the key thing to understand, to solve this problem, because it didn't ask the pressure at the bottom, it didn't ask the pressure at this point, right? It asked the pressure at this side wall. So we have to do integration and get the final answer. Okay. I hope you understand, all of you understood this problem. I try to do my best, and if you have any questions, you can come to the office hours